Finally, we would like to thank and acknowledge our sponsors, DC3 Dreams and Boise Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boise Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. All right, now, some of you in the audience might remember Dr. Barbara Harris's excellent how-to hour on the topic of DSLR photometry back in March. Well, today's instructor wrote the book on the topic. That is to say, he helped draft the DSLR observing manual, and he's been observing variable stars for years, not just with the DSLR, but also with CCD cameras. As a matter of fact, he's been doing CCD photometry since the 80s and is now a true expert when it comes to this precision technique. He's been an AAVSO member for about a decade and is currently serving on the AAVSO board. Ladies and gentlemen, without any further ado, please allow me to present your instructor for the day, Mr. Bob Buchheim.
Thank you very much, Lauren. And okay, guys, regarding my expertise, I was looking at who signed up here, and I see some names, Jerry, Dennis, Ed, Gary, Joyce, who know at least as much about photometry with CCD as I do, and maybe more. So if I can't answer any question, they can help when we get to the Q&A portion. There we go. I'm in slideshow mode. As Lauren said, we're here to talk about getting started at CCD photometry. I'm going to assume that most of you have some sort of a telescope and mount and CCD camera, and that most of you can take some sort of an astro image, setting aside issues of beauty and quality, and that you're curious about making photometric measurements with your CCD imaging setup. Maybe you've tried it in the past and been discouraged, but you just can't let go of the idea. I'll show some slides and pontificate for about a half hour, and then we'll open it up to talk about questions, topics that interest you. As Lauren mentioned, if you have any questions while I'm talking, type them into the Q&A box. If it seems appropriate, she'll step in and we'll deal with it right then, or we'll handle it during the Q&A discussion. I am on the AAVSO board, but disclaimer, what I'm about to say is not an official AAVSO position. I'm going to talk about things I learned when I was getting started, and I'll admit that some of it may be a little bit of heresy, so take your chances. When I started out, I learned some hard lessons and came to two fundamental notions for someone who wants to begin doing CCD photometry. The first is use the equipment you have, get an initial experience, then start thinking about special purchases devoted to your photometry. And number two, don't overthink this. Just try it. You'll make some mistakes. They'll probably be pretty obvious once you see them, and you'll learn from them so that your second attempt is likely to be something that you're proud of. Then you keep learning and improving over and over for the rest of your life. Let's look at a astro image of a collection of stars. Those of you who have done something like this understand how to get focused, how to aim at a target. get your tracking and guiding working, and then take another image and another image of the same field or object. I'm not going to talk about that. I'm going to assume that you have some experience in that. We can delve into it in more detail if necessary during the Q&A session. And you look at an image like this and you see what you see. You see some stars, the white dots. You see that the background is not perfectly black. That's a combination of skylight, sky glow, and dark current in the CCD system. If you look carefully at this image in the lower left and lower right corner, you can see evidence of vignetting in the optical system, how the background kind of fades to a little darker dark than it is over the rest of the image. By the way, Lauren, are the screenshots of you and I interfering with the slides?
Sorry, I had to unmute. They are not from my point of view.
Okay.
However, if any of the attendees find that they are, that the little video thumbnails are interfering, then if you hover over them, you are able to collapse them to a tiny little bar with the little option up at the top.
Perfect. Thank you. You cannot see in this image, but there is in it the effect of dust donuts in the optical system. And if you've done any aster imaging, you understand the notion of dark frames and flat frames and how important they are to making a beautiful, good quality astro image. They are at least as important when you're going to do good quality, accurate photometry. Base your darks on a lot of darks that get average or median combined. I routinely take 25 darks to median combine into a master dark. Similarly, 25 flats, median combined into a master flat. This image shows a contrast enhanced picture of a typical master flat from my photometry setup. You can see dust donuts of different sizes and strengths kind of scattered all over the place, typically giving about a 3% loss of light in the donut, and that would naturally translate into a 3% error in photometry if it wasn't corrected by proper flat fielding. And you can see the impact in the lower left and the entire right-hand side of the image of a little bit of vignetting in the optical train, amounting to as much as 12% drop in light out in those corners, again, which would translate into a 12% error in your photometry if it wasn't corrected properly. As you know, you take your image processing software and give it both your darks and flats and your raw images, and it will process your raw images, subtracting the master dark and dividing by a normalized master flat to give you a processed image. Example shown here. The dark signal is gone, the effects of dust and vignetting are gone, and indeed the very small pixel to pixel response non-uniformity is also taken care of by the flat. So now you have a smooth, clean image, and you're prepared now to start doing photometry. Differential photometry asks a real simple question. Is star number 1 brighter or fainter than star number 2, and by how much? You are required to have at least 2 stars whose brightness is well known from a calibrated catalog, plus your target in the field of view in order to address that question. And we'll talk about how to deal with those. And we'll talk about how do you actually do this. The concept of differential photometry is pretty straightforward in principle. The photometry software that you use, MaximDL, AIP for Win. If you're an AAVSO member, you can use AAVSO's online vPhot software. There are a variety of others that will do the job. Your photometry software is going to do all of the calculations for you, so I'm not even going to show you the equations. You'll find them in reference material. And as you gain skill and experience in CCD photometry, you will come to love them. But for now, let's talk more about the procedure. You'll open up your image of the target field. You'll place a bullseye, as shown here, over your target star, another one on your comparison star, and another one on the check star. You'll tell your software what the standard calibrated magnitudes of your comp and your check star are. And the software will then look at each of those star images and add up the total amount of light coming in from the star, subtract the associated skylight, and compare the stars. If it decides, for example, that your target is a half of a magnitude fainter than your comparison star, delta mag equals 0.5, and your comparison star is a 9.0 magnitude star, that means your target is 9.5 magnitude on the night that you measure it. The bullseye that you're putting on, shown in this little image, consists of an inner circle called the measuring aperture. Its job is to collect all of the signal, all of the ADUs on all of the pixels that are inside that circle. And if you think about what's going on in there, each pixel inside there is receiving light from the star, but it's also receiving light from the sky glow. So you need to separate the sky glow from the star, and that's the purpose of the outer two rings called the sky annulus. The software will go through, look through here, and determine the average sky level per pixel, do the subtraction, do the arithmetic. Your job is not to sweat the math. As I mentioned, your software will do it correctly. Your job is to sweat the details of how do I make a good image for photometry? How do I select the measuring aperture and the sky annulus? And how do I identify and select the target and the comparison and the check stars? We'll start with that last item. The most fundamental feature of a good image for photometry is that it contains your target and it contains a comparison star and a check star whose standard magnitudes are known. Best way to identify those in your image is go to the AAVSO website, homepage, resources, pick a star, enter your star name in the box, and then click on Create a Finder Chart. And what you'll find is something like this. A chart that shows the star field. The tool will allow you to adjust the field of view of the chart and the orientation of the star chart so that it matches your images. And then by eyeball, figure out which stars in the chart are which stars in your image. The symbol at the center of the chart, that's the position of your target. And the little numbers on some of the dots, some of the star images, indicate that those stars have well-calibrated standard magnitudes. For example, this star is a 10.0 magnitude VMAG, good choice for the comparison star on this particular target. And this star here is a good choice for a check star. It's 9.8 magnitude. So now you know where your target and your comp and check stars are. The image must also be in FITS format in order for all of the commercial software packages that I'm aware of to do photometry on it. AAVSO's vPhot also requires that it be in FITS format. And I think every commercial CCD control software will give you FITS format as an option. One of the key things about the FITS format is it's a data block that shows essentially what the image is, plus a header block that contains information the software will need about the way the image was taken. As a minimum, the observation date and time, and most camera control software will also write a lot of information, the pointing direction, target ID, nature of the telescope, nature of the camera. A lot of parameters go into most FITS headers. Instructive to look at the FITS header from your camera if you haven't stared at it for a while. The next most important feature for your photometry image is that these stars, the target, the comparison, and the check star, be not saturated and be in the linear range of your camera. This topic is probably the most important one that I'm going to mention for quality of photometry. The terms saturation and linear range relate to the way pixels on your CCD respond to light. Start with the image of the star. The little picture is in the upper right-hand corner of the slide. And imagine taking a cross-section of the signal through that image of the star and plotting signal on the pixel in ADUs on the vertical axis and the X position, pixel coordinate on the Y, or on the X axis, I'm sorry. Most of your image processing software will be happy to make such a plot for you. If you tell it, this star, please show me this cross-section plot of the star image. And you'll see that your cross-section profile looks like this little sketch. It's tall in the middle and it fades away to the left and right, a stereotypical star image. The technical name for this is the point spread function. The width of it is set by the resolution of your optical setup, the size of the pixels in microns, the local atmospheric seeing, and a few other things. Generally, all of the stars in your image will have an identical width, described here by the yellow arrows, the full width at half maximum. However bright the top of that curve is, come halfway down and measure the full width. All of your stars will be very similar in that measure. Now, if you imagine a brighter star than this, or this star taken with a longer exposure, naturally more light is coming in, and as a result, the height of this curve and the area under the curve, which are set by the total amount of light in the exposure, will change. So if I look at a brighter star, or I just take a longer exposure of this star, I'll get a point spread function that looks like this. Brighter still, it'll look like that. But at some level, when I expect to see a point spread function like this, bright star and or long exposure, I expect to see that dotted red curve, but what I actually see is this, a flat top on the point spread function. What's happened is as photons, light comes into a pixel, the pixel in effect converts them into photoelectrons and accumulates those photoelectrons as they are generated for the duration of the exposure. But the pixel can only hold so many electrons. And once it's full, that's all the signal that it can read out. That's all she wrote. There ain't no more. And so you get a flat-topped point spread function on that star in that exposure. And that is diagnostic of a saturated image of a star, and you cannot do good photometry with our commercial software on a saturated star image. So that means either you need a shorter exposure, or if this is your comparison star, you need a little fainter comparison star. There's another way to explain what's going on there or to visualize it. Again, light comes in as photons. They're converted to electrons, which are counted and read out as ADUs. And more light in during the exposure means more signal in ADUs. And so as light comes in, the ADU signal goes up. And one of the wonderful things about CCD sensors is this is a straight line kind of a response curve up until the point where the pixel is full, at which point no more signal increase no matter how many photons come in. You know, you can sort of think of it as you're filling a bucket, and every time you put another cup of water in it, it's full, that cup falls out and the bucket stays full, but it can't get any fuller. The kink in the response curve, again, is the saturation level. Real CCDs have a somewhat more gradual transition from the linear region to the saturated region. Rather than having a sharp kink in the curve, there's a kind of a gradual bend over in the curve. And what that means is where this yellow arrow is, at that intensity level, you start departing from the linear response. More light in is still more ADUs, but at a lower rate. And that linearity assumption is built into all the commercial photometry software that we use. And so what that means is, in order for the software to give you a good answer for that question of, is star A brighter than star B and by how much, all of the star images you're using must have a peak pixel signal that's lower than indicated by that first departure from linearity in the response. The neat thing about this view is it gives you a clue of how to measure that for your own camera, which you should do. If you already use a light box or a flat panel to do your flat images, set it up, take a short exposure flat image, one that barely shows you some light on the image, save that, take another one at a little longer exposure and another at a longer exposure yet, and keep doing that until you reach the point where increasing the exposure doesn't increase the signal. That probably for a 16-bit camera will happen around 60,000 ADUs per pixel. And now look at each of those images and say, look at the average signal in the middle portion of that flat image, and plot on the x-axis the exposure of the flat, and on the y-axis the average signal in the middle of that flat image. And your data points will fall on exactly this kind of a curve. Longer exposure, more ADUs, until you see it turn over and finally saturate. So you have now measured the maximum ADUs on your camera that are within the linear range of the camera. If you don't use a light box, you could do the same kind of thing with a star field. Start with a short exposure, take a 15-second exposure, and then a 20, and then a 30, and then a 40, and pick a star or two in the images and look at the maximum pixel in the star image and plot max pixel as a function of the exposure duration. And again, you'll plot out exactly this curve. If you use a star field, your data points will probably be a little bit scattered because of the way seeing and atmospheric extinction and things like that change a little bit over the course of your experiment. But if conditions are reasonably good, you'll be able to see exactly what I'm showing here in your own setup. As I mentioned, critical concept, linear range and non-saturated stars for your photometry. You will also hear reference made to adequate sampling of your point spread function. The term refers to the size of your star image in pixels. That full width half maximum, the size of your typical star image, must cover at least 3 pixels in order to be properly sampled. Less than that, and there are a variety of artifacts that are going to reduce the accuracy and precision of your photometry. If anybody wants to, we can talk more about the details of why is it 3 pixels across the width of the star image during the Q&A. If, as it turns out, your stars are smaller than 3 pixels, maybe you're using a relatively short focus refractor, short focal length refractor, or maybe you've got a focal reducer and relatively large pixels in your camera, you could easily have a situation where the typical star image is only 1.5 pixels wide, maybe even less. What do you do? First thing you do is take the focal reducer out of the setup. That'll lengthen your focal length. That'll make the star images a little larger. In a pinch, defocus a little bit to make the stars a little more blobby, get them to that 3 or 4 pixel goal. This is one of the differences between imaging for photometry and imaging for beauty. Your small, perfectly focused image stars in an image of a globular cluster or a nebula is the cat's meow. It makes the image look sharp, whereas this little bit of defocusing I'm talking about is going to make the image look kind of blah. In fact, the combination of well-sampled star images and not saturating any of the pixels in the image means that your photometry images, compared to your beautiful astro images, your photometry images are going to look washed out, faded, and plain ugly. Because what we're aiming for here is scientific measurement, not beauty. There's a different kind of a beauty in the scientific measurement. While we're looking at this, let's also address the question of how large should I make the measuring aperture and the sky annulus in my photometry software. All of the commercial photometry packages ask you how big should the measuring aperture be, and how big should the annulus be, and how big should the gap be. Regarding the measuring aperture, remember its job is to collect all of the starlight and not too much surplus sky background. So how big do you make it? Well, big enough that it captures all of the starlight, the full point spread function, but not too big because there's no point in capturing a whole bunch of pixels that are filled just with sky glow. So that's the answer, big enough, but not too big. The sky annulus, remember, its job is to give you a good measure of the average sky brightness in your image. In order for the averaging to be effective, most people recommend that the area in that donut should be at least double the area in your measuring aperture. So dredge up your high school geometry and figure that out. The other important thing is that you don't want any bright stars within the annulus, because its job is to tell you about sky glow. So you make the annulus width big enough that it has a total area double or so what the measuring aperture is, and then you pick the size of the gap and the size of the thickness of the annulus such that there are no bright stars in there. You don't have to be totally meticulous about making sure that there are no stars in the annulus, because all the commercial software examines all the pixels. It will recognize if there's a little star in here and it will ignore those pixels. But don't have a big bright one in the sky annulus. Now, at this point, finding your target, determining your comp and check stars, worrying about linearity and saturation, worrying about sampling of the point spread function, you might be beginning to fear that you're in over your head. I understand that. The hard truth is that both the theory and the practice of photometry can appear overwhelming, but you don't have to learn everything all at once. And you don't have to take on the most challenging project in the beginning. Remember my fundamental principle. Use the equipment you already have and just give it a try. Start with a pretty straightforward project. Something's not too stressing. And I tell you, there are plenty of stars that need your attention that are relatively easy to measure, and they're not being covered sufficiently. Everybody started out as a beginner, and there are plenty of useful projects even while you're still building your skills. Both of the people on this slide are having fun. Both of them are pushing their own personal boundaries. Each of them is going to fall down occasionally. They're going to learn something each time they fall. And in the process, they're not going to hurt the ocean at all. In the same way, give a try at stellar photometry. You're probably going to mess up occasionally. It's not going to hurt the star. Look critically at your data, and you'll learn from your mistakes. And because you're looking at your data critically, you're not going to submit subpar information to the AAVSO database, but the data that you do submit, you'll be confident is good quality and a real contribution to science. Where do you start? There are a variety of philosophies on answering that question of what star should I pick? What should I do for my first experience in CCD photometry? And all of them are well-founded. There are a variety of good answers, so I'm going to give you three of them. One philosophy is start off with a well-observed long period variable star. For example, here's a light curve of R Leo spanning about a 2-year period of time. The V-band CCD images photometry is the green squares, showing that the star right now is kind of near its minimum light of a little fainter than 10th magnitude. The advantage of using a long period variable as one of your first experiences is if it's a well-observed star like R Leo is, it's easy to compare your measurement to that of other experienced observers who are observing it at practically the same time you are. And that will either highlight some problems in your photometry that then you can go fix, or give you some confidence that what you're doing is working and the answers that you're getting are correct. And it doesn't require that somebody observe this star on exactly the same night as you did, because the star doesn't change that much over the course of a few nights or even a couple of weeks. So it's easy to compare your results. And if on your first night you discover that you messed up in some way, you can take corrective action, go back the second night, and the star is going to be in the same place and essentially the same brightness as it was on the night before. So it's a lot easier to compare your results with yourself. On the other hand, these are almost all strongly colored, very red stars. And that means if you do not use a colored filter, ideally a photometric Johnson-Cousin V-band filter, then you're going to be, your photometry is going to be influenced by color effects and the fact that the spectral sensitivity of your camera is a little different from the spectral sensitivity of the standard photometric band. So you may see some offsets between your measurement and the reported green squares on this curve. You're also a little bit at risk of atmospheric effects when you're not using a filter in your system. Maybe, you know, I mentioned it's good that the star doesn't change very much because you can compare tonight's result and last night's result carefully. But the downside is there's really no action. If everything is going well, you measure it tonight and it's 10.1 magnitude, and you come back tomorrow and it's 10.1 magnitude. That's good science, but it may not give you the emotional charge that you'd like from variable star observing, because it doesn't seem to vary very much from night to night. On the other hand, our Leo, I picked for this example because it's perfectly positioned for observation tonight and for the next month. Leo is straight overhead for us North American observers and I guess the entire Northern Hemisphere for the next month or so. So you can get several hours on this star and you can come back to it night after night as you improve your skill at CCD photometry. But if you want a little more action, an alternative is to pick a well-observed eclipsing binary star, like this example, EM Boötis. Or you get similar action from many W-UMA binary systems, or from many high amplitude delta Scuti pulsators, or from some RR Lyra type pulsators. EM Boo, again, is perfectly placed for observation right now. It's high in the east at astronomical twilight. You can get on it, take a few test images to set the exposure properly for your camera and telescope, and then just take a series of exposures for 3, 4, 5 hours. Spend a night with this star. If you're watching it on the night of an eclipse, you see some action. Here's an eclipse light curve in V-band of EM Boo. In the course of 2.5 hours, it dropped by 1/4 of a magnitude. Unmistakable. And if you observe it on the night of an eclipse, and if you catch the fall, the flat bottom, and the rise out of eclipse, you can measure quite precisely the midpoint time of the eclipse. And that turns out to be an important scientific datum for the study of these eclipsing systems. Some of them, the eclipses happen right on schedule. Others, the ephemeris of the eclipse sort of wanders in time, because in addition to 2 stars going around each other, there's something else going on in that system. In some cases, there's pretty good suspicion about what it is. In others, it's kind of unknown. And AAVSO has a program to collect these eclipse timings. Plus, the timing of the eclipse and the visual effect of the brightness drop in the eclipse is relatively insensitive to whether you're using a filter or not. If you're not using a filter, then what you measure as the minimum magnitude will probably not exactly match the V magnitude as shown in this graph, and the out of eclipse magnitude, the 9.02 mag, will probably not exactly match what you're seeing. But the delta magnitude, the amount of the drop, will probably be very, very close to what you observe even unfiltered. What can go wrong? Look at the orbital period. EM-BOO has a period of 2.45 days. So it means that the eclipse only happens every 2.45 days. And what is that, about not quite 60 hours. So there's no guarantee that you're going to see an eclipse tonight. On the other hand, go to the AAVSO website, look at the VSX detail on the star that you're interested in, and it will give you an ephemeris. It will give you a prediction of when the eclipses are occurring. And then you can ask, is the star both above the horizon and in the dark when the eclipse happens? And you can pick your observing night that way. This mapping the eclipse also requires time series observation. It's not a one image and done project. You're going to take a series of images over several hours, but that's for many setups not a extraordinarily difficult thing to do. And you get to see some action on a variable star varying in your data on one night. A third philosophy is make your first experience with photometry the observation of a field where many stars have known calibrated magnitudes. And you can take a series of images. M67 is an open cluster that meets that criteria. There's probably 40 or 50 stars in that cluster, ranging from I think a little bit brighter than 10th magnitude down to 14th or 15th magnitude, all of whom have very well calibrated brightness. And so you take some images of this, pick one of those known stars as your target, pick another couple of them, one as your comp, one as your check, and then do your own calculation based on the comparison and check star you picked, calculate what the observed magnitude of the target is, and compare that to its known calibrated magnitude. You can do that for several stars of different brightness and different color, and give yourself both an understanding of exposure versus magnitude to stay in the linear range, etc., of your sensor, and an assessment of both the precision and accuracy of your photometry in a way that will give you improved confidence in your photometry, and also tell you some important information about the color response of your CCD, a topic I'm not going to go into, but measuring M67 on occasion, say once a year, is a really good discipline. Obviously, the drawback is it sounds a little boring and a little bit tedious to measure stars that are already well known and not variable, but it's a great learning experience to gain both skill and confidence in your photometry. And if your system is able to go a little faint, there's a gem hidden in there. Right in the middle of the cluster is variable star AH Cancri. It varies from magnitude 13.3 to 13.69. I don't remember what the cycle time is, but as I say, if you can go that faint, there's even a little action hidden in this otherwise tedious project. Okay, I'm done pontificating. Let's see if we have any questions and what you all would like to talk about.
All right, thank you very much, Mr. Buchheim. That was great. All right, so our first question that we're going to cover is about calibration of photometric images. So Kate Britton had asked, do you need bias frames?
Yes and no. Since you asked the question, you probably know about scaling your darks, pretty commonly done in most astroimaging. If, for example, your photometry images are 2-minute exposures, but you already have a dark library of 4-minute exposures, If you also have a master bias frame, then you can scale the darks to match the exposure of your science image. Absolutely works, absolutely a legitimate approach. But as more and more people are migrating to CMOS sensors, my understanding is it doesn't work, scaling the darks doesn't work very well with CMOS. So if you have a true CCD camera, yeah, go ahead and scale your darks if that's more convenient than having darks taken at the exact exposure of your science frames.
Okay, thank you very much. All right, so speaking of CMOS, we had a couple questions come in about that. One was from Mike Gardner, who simply asked, if I'm using a CMOS camera, how much of what you have told us is applicable?
I don't have experience with CMOS, but from the reports that I have seen, it's all applicable. And in fact, it was thinking CMOS is why I talked about darks, but not bias frames. The one thing about CMOS is that apparently something about the way they respond, scaling the darks is a bad idea. But make your darks the same exposure duration as your science frames, obviously the same temperature for your darks and your science frames. Do flat frames just like you would with a CCD. One other thing about CMOS that if you're using one, you may already be aware of, even the ones that advertise themselves as 16-bit readout, they're sort of not. They're really two amplifiers of either 12 or 14 bits each that are scaled. And I've seen reports of a sort of a kink in the response curve on some of them because of that. On the other hand, they have practically zero read noise. And so some people recommend that do your linearity measurement. You might find that the linear range of the CMOS chip is shockingly small compared to what you expect in a CCD, tiny pixels, things like that. But, and maybe, whatever stars you're dealing with, you're really only confident taking a 15 or 30-second exposure to be within the linear range. Fine, just take a lot of them. If the signal level is not to your liking, take 10 of those 15-second exposures, and now you've got 150-second summed exposure, and you're not adding any significant amount of read noise. So that's more than I know about CMOS.
Thank you. All right, so next up, we had several questions come in that were asking about what is the difference between check and comp stars?
Good question. I sort of glossed over that because in many ways they're serving the same purpose. Remember, you've got a target, and you pick a star whose magnitude is known, and you compare. Target minus comp is the equation that the software is doing. But, even the best observed comparison stars every now and then are discovered to have, oh my gosh, they are variable after all. If you're familiar with the Landolt standards, there are a couple of stars in Arlo Landolt's papers that had been used as standards for a decade until somebody noticed, oh golly, it's an eclipsing binary, and once every 6 months it dips by a healthy fraction of its light. So how would you know if you picked one and it was misbehaving that way? The answer is, that's where your check star comes in. You have your target, your comp, and a check. And so you monitor, is my target changing relative to the comp? That's the variability that I'm looking for. But if my check star is also varying, We all see this occasionally where you go, wow, my target is going up and down and up, and my check star is going up and down and up and down in exactly the same way. Well, what that's telling you, it's not the check and it's not the comp, it's your comp star that's going up and down and betraying itself in the distorted photometry. So that's the difference. You use them exactly the same way. The check star is called check because it's your way of checking that the comp is in fact non-variable in brightness.
Thank you. There was one other kind of facet to that question, which was what are the characteristics of a good check and comp star, and how do you select good check and comp stars?
Yeah, good question. There's a whole art and science to that. Ideally, for a particular target star, which means that target star has a brightness range and a color range. Ideally, the comparison and check stars would be similar to the brightness of the target, not too bright, not too faint, say, within a magnitude or less of them ideally, and very similar in color. And the color business shows up in two ways. If you watch the sunset, when the sun's overhead, it's a sort of a yellow ball, and when it's setting, within 10 degrees of the horizon, it becomes red. Its color changes. Well, it's not the sun, of course. It's the atmospheric extinction, which scatters blue light preferentially, and so only the red light is left to come to you through that long atmospheric path. Well, this exact same thing happens to stars. A warm yellow star, a sun-type star, when it's up near the zenith, is warm and yellow. But as it sets and it gets close to the horizon, its color changes. Now, its color is shifting. There's also the spectral response of your observing setup, which is fixed. And so brightness can be either shifting out of your spectral band or into it, depending on whether your response, shades toward the blue or toward the red. If the target and the comp star have identical colors, then that color shifting will be almost identical between the two of them as they set. And all of that, this whole concept of differential photometry is based on the assumption that you're not using a really, really wide field of view. Think in terms of less than a few degrees field of view. So your comp and your target are close to each other, which means that wherever you're pointing, if you're aiming 40 degrees above the horizon, for practical purposes, they're both at 40 degrees. For really meticulous measurements, there is a science to compensating for, you may have a 2-degree field of view and, my comp may be at one end and my target at the other end of the field. So they may actually be at a half a degree different elevation angle above the horizon. There is a science for compensating that you'll learn as you progress in photometry, but for easier targets, you can act as though a few degree field of view, atmospheric effects are uniform across the field. Don't go, say, lower than about 30 degrees above the horizon, with all kinds of atmospheric effects come into play then.
Thank you. That's a good answer. All right, we had one more question here about comp stars from Patrick Selip, who asked, if there are no known comp stars in your field of view, can you use something else?
Yeah, there are fields where the AAVSO charts are pretty sparse. And particularly if you have a relatively narrow field of view, you may actually find some variable stars that you just can't find a decent comp star. That was the prime motivator behind the APAS, AAVSO Photometric All Sky Survey. There are still a few pieces of sky that don't have good APAS stars in the field. A year ago, I worked a variable star. You look at the APAS map, it covers the entire celestial sphere, except for this little spot right here, right where my star was. So if the AAVSO chart doesn't show good comp stars, APAS will, and searching APAS is a pretty clean process on the AAVSO website. Failing even that depends a little on the nature of your project. If you're measuring eclipse timings of an eclipsing binary, the exact amplitude, magnitude of your comp star is sort of unimportant, because what you're interested in is the fall and the rise in the eclipse, and you're measuring the time, not the brightness. So a project like that, it doesn't really matter. You pick a random star in the field that looks about the same brightness and about the same color, if you find color information. And for targets that are faint, the cataclysmic variable studies are sort of a poster child for this. All of the targets tend to be faint, so all of the observers use unfiltered CCD photometry, and the professor who analyzes the data doesn't worry too much about what comp star you picked, because just because you're unfiltered, every observer is going to have a kind of a personal offset in photometry, and Dr. Patterson just corrects them all to a standard baseline. Okay, so that's more information than you wanted, and I've kind of forgotten and if you don't have a comp star, shy away from sources like the GuideStar catalog. The photometry, as I recall, is notoriously bad there. The APAS is your go-to source for most targets.
Thank you. I would like to add on to that real quick that the AAVSO observing section webinar for the exoplanet section that was held earlier this year did cover some of that, because they were talking about detecting exoplanet transits and using non-standardized comp stars just to detect that transit, like Mr. Buchheim was just talking about. So you can check that out.
Yeah, and it's good methods, and they're looking for really, really small, 1% or less changes in brightness. So that's a very challenging photometry project that you can succeed in.
Yeah. All right. So next up, I think we should talk about filters. We're having quite a few questions about filters come in. So the number one that I'm seeing repeated here is starts with a comment that Johnson-Cousins filters are not available at the moment, and asking what are the alternatives. So here we have Jay Miller asking, he'd said he'd bought a Sloan G filter, but the AAVSO doesn't seem to accept that. So what are his options?
I'm surprised. I'm surprised of the comment of not AAVSO not accepting G, because APAS provides G, R, I, and Z measurements. Well, okay. I guess I'll take a pass on that. I know that the AAVSO is happy to take U, B, V, R, and I, and tricolored B, G, and R. I'll have to take a pass on that.
All right.
But the more important question is, where do I buy one? Yeah, and that has become a real challenge over the last year. I think Chroma and Illuma might be still making Johnson-Cousins filters. If not, the Sloan filters are probably slowly becoming the de facto alternate standard.
Okay, thank you. All right, so speaking of alternate filters, we had a question here that said that all of the filter sources he had checked were out of stock except for Chronos filters, and that the Chronos filters are high transmittance interference filters that have a rectangular bandpass, not the traditional Johnson-Cousins bandpass. What do you think of that?
Probably better than nothing. But if you go that route, as the market may kind of force you to, the flat top high transmission rather than a Johnson Cousins, which is a more smooth wavelength versus transmission kind of curve, you'll have to get really comfortable with transforms, which is the way that you adjust your photometry if your spectral sensitivity curve is a little different from the one that Johnson and Cousins used when they made their photometric measurements. Transforms is the way that you characterize and adjust your system's measurements to the standard photometric system. And I suspect that those flat top guys transform reasonably well.
Okay, thank you. We had a couple of questions that were asking, what is the point at which one should start to use filters in their journey into photometry?
I'd say as soon as practical. A year ago, I might have said, oh, come on, the V-band filter only costs, what, $100, go get it. But the market has dried up. So as soon as practical is definitely the answer. Maybe you can get a Sloan G-band. Take a look at the filter transmission curves of Johnson Cousins and the Sloans, and the typical sensitivity curves of CCDs, and you'll understand why you'll get different photometric results depending on your filter and the color of the star and your system response.
Thank you. All right, a couple more questions here.
By the way, the Astro Imagers RGB sets are, I think, readily available on the market. And I have seen papers about transforming from the G Astro imaging filter to photometric V. Not bad. It's doable, and it'll give you an opportunity to learn all about transforms.
Great. That was actually one of our next questions coming up, so I'll check that one off.
There are probably references on the AAVSO website on that subject of imaging filters and transforming to V-band. Search around on the website and you may find it. There have also been a few papers presented at the Society for Astronomical Sciences over the year on that subject. And my recollection is that generally the transformation worked very well.
Yeah, I seem to recall coming across those resources you talked about, like a tutorial on transformation that might be in the CCD Photometry handbook.
Could be.
That would definitely be something. If you're interested in using alternate filters, go check out the website. All right, so Patrick Kavanaugh had asked, once we go out shopping for CCD and filters, which should be first to find, the camera or the filters? I ask this because there seems to be a scarcity of both CCD cameras and filters.
Oh man, hi Patrick. Yeah, I'm probably not the guy to make any recommendations on that. I'm still using an S-Big ST8, which must be 15 years old, but it's a real workhorse. And the modern CCD chips are getting large. And that means that your filter needs to grow so that you don't get excessive vignetting around the image from that large, they're now as big as a 35 millimeter camera frame. And that in turn might force you to the 50 millimeter filters, ka-ching, more dollars, and a filter wheel that can handle them, ka-ching. So yeah, talk to your friends in the imaging world and the photometry world and see what is new on the market.
Right, thank you. We've got just a couple more filter related questions and then we'll move on to a different topic. The next ones are asking about using alternate commonly available filters such as a UV IR cut filter that passes from 400 to 700 nanometers and or a light pollution filter.
The first might be an improvement because at least it gets rid of the most strongly colored, the deep blue and the deep red. You probably still need to transform to get proper V band magnitudes, but certainly if you already have one, certainly a worthy experiment. I would say probably not to the light pollution filters because I think those tend to be very narrow band. You can get what they call nebula filters, for example, and those are very narrow bandwidths centered on the characteristic emission lines of the nebula. I have no idea how they may transform, but it doesn't sound like the best approach. If you already have one, give it a try, but I wouldn't stake my life on it.
Mm-hmm. Just speaking from my own experience with spectrography, a narrow band nebula filter is probably more likely to harm than hurt because they're often centered on lines such as the hydrogen lines, which in stars can be in absorption and varying from star to star, even if the stars themselves aren't different in regular photometric filters. So you'd probably get a lot of false signal there.
Yeah, good example. Yeah, it'd be dangerous at best.
Yeah, probably best to go unfiltered if all you have is a narrow band light pollution filter.
Yeah.
All right, one more question about filters, and I don't expect you to be able to answer this one, but we got a question asking, when will good V filters be available?
There's a risk that the answer might be never. The demand is small. The manufacturing process is meticulous. I hope they come back because it's been the standard for so long. But I don't think Astrodon, Custom Scientific, I think is completely out of business. Chroma, I don't think they're advertising a return to production date, which is a little spooky.
All right. All right, so moving away from filters now. We had a question asking about calibration again. Do you take the calibration images all at the beginning of the session, all at the end? Do you split it up with taking half of them at the beginning, half at the end? What would be the best practice?
For most cameras, there's no reason that you need to take darks every night. I think CCDs are pretty darn stable, and so you can take a dark library and probably use it for a month or more. I refresh mine every couple of months, or if the camera's been off the telescope for a while. Flats are a little bit of a different deal. Anytime there is any change in the optical path, you need to refresh your flats. And that includes if I just removed the camera and put it back in, now it's in a little different orientation relative to the lenses and mirrors in the telescope. So anytime there's a change in the optical path, you need to take new flats. And if you have a filter wheel, you need different flats for each filter position.
All right, thank you. So our next couple questions here are about binning. Does it make sense to use binning? And if you do use binning, do you need to recheck the linearity?
Yeah, my recommendation is do not bin. For your photometry, run the camera one by one. And the reason is if you bin, say 2 by 2, so you've taken 4 pixels and mushed them into one number. If one of them is saturated, you'll never really know. It'll be affecting your results, but it's really going to be hard to tell. And if you bin 2 by 2, that star image that used one-to-one binning had a full width half max of say 4 pixels. Well, you bin 2 by 2 now, it's barely adequately sampled. And so why take that risk? The only real advantage to binning when you're looking at stars is it makes your file sizes a little smaller. But modern computers, whether it's a 10 megabyte image or a 50 megabyte image, they're going to swallow it just fine. If for astro imaging, people often advise binning, particularly in the luminance image, because by binning, you get more signal in each of those bin deals. But that's kind of not true with stars. A nebula is an extended source. Star is a point source. So I would encourage you to don't bin.
All right, thank you. I'm going to guess then that that's the reason, that's the answer to our next question, which was why does the AAVSO photometry guide recommend not binning over 2 by 2?
Yeah,
so,
that's why.
All right. So our next question is from Christian Sukyu, who asked, what ADU should you target for your stars?
Good question. Difficult to answer. The ADUs, peak ADU should absolutely be below the linearity to saturation limit. On the other hand, the more ADUs in the star signal, the better the signal to noise ratio, which I guess we can talk about if anybody really wants to. And for any given star, the way you increase the signal is you take a longer exposure. At which time, depending on the nature of your target, you need to ask yourself, which is more important, getting more signal or getting better time resolution? If I'm looking for a change that happens over 15 minutes, well, then I can't use an exposure longer than probably 3 or 4 minutes. But if the star is faint, well, I may need to take a longer exposure to get a good, accurate measurement. So that's a long way around saying it depends on the situation. But all other things being equal, take a look. Most of your photometry software, when you put your measuring aperture on the star, it will try to give you an assessment of the signal to noise ratio and the photometric accuracy. And if the photometric accuracy says, boy, plus or minus 0.2 of a magnitude, that's probably not good enough. Increase your signal level and that photometric accuracy might become 0.05 magnitude, which is kind of more where you're shooting for most of the time.
All right, thank you. All right, we're going to take a couple more miscellaneous questions right now from this one from Mark Harris, who asked, how much of an issue are satellites crossing your images?
My personal impression is that is a catastrophe that happens once in a million times. It's like worrying about getting hit by the killer asteroid. I have occasionally seen a satellite trail across one of my images over the years. I see airplane trails much more frequently. The much maligned Starlink network, thousands of satellites. Well, once you're well past twilight and you're looking pretty much upward in the sky, they are black. So I may be proven wrong eventually, but I don't see that as an issue worth worrying about.
Thank you. All right. Next question is about moonlight. Is it worth observing on bright moonlight nights? Can you get good photometry when the moon is full?
Yeah, you can. Like any other measurement, when the background level, the sky glow from the moon rises, there are a whole lot of things where it cause random noise to go up also. And the light of the moonlit atmosphere is a pretty different color than most stars, so there's effects there. But on the other hand, remember your sky annulus is there to subtract out the sky glow that's within your measuring aperture. You're going to probably say, well, I'm going to look at my brighter targets on a brightly moonlit night, and probably, depending, this is going to be very instrument specific, but as you look closer and closer to that bright moon, the brightness of the night sky is no longer a uniform brightness, but it's way brighter over here than it is over here. And that kind of messes up the whole theory of the sky annulus and subtracting the sky glow. I could, with my C11 with a dew shield under a dome, I could probably get within 20 or 30 degrees of a almost full moon and get decent photometry on a decently bright target, 10th, 11th magnitude. So your mileage may vary, but the moonlight is not an absolute killer.
All right, thank you. That's good to know. Okay, so Dali had asked, how much do we defocus to be within the 2 to 3 pixel width? Is there a methodical way, or do you just simply do trial and error?
Yeah, well, it's obviously much simpler if you have a motorized focuser. And in that case, you get sharply focused and then you move it off a titch. When I've had to do that, what I do is start by getting perfectly focused, see what your full width half maximum is. So now you say, okay, it's 2 pixels and what I really want to get to is 4. And just tweak the focus a little and then remeasure your full width half maximum. Don't overdo it too much. If you have a Schmidt-Cass or a Newtonian or a Ritchie-Chrétien kind of a telescope, as you know, as you defocus too much, your star image now becomes a ring. And that gets kind of confusing for your photometry software. You still want the star image to look kind of a roundish blob. So that it's a trial and error thing. You have to get used to your own equipment. After a while, you'll know I need to get focused properly, and then 1/8 of a turn of the focus knob will put me where I want to be.
All right, thank you. Speaking of Schmidt-Cassegrains, we had a couple of people asking if telescopes with really small fields of view, such as Schmidt-Cassegrains, are useful to someone who's just starting out.
If you already have one, I would say use it. One of the things about the commercial Schmidt-Cass, the Meads and Celestrons, et cetera, is they're f10 telescopes. What that means, pretty long focal length. If you have a CCD camera with small pixels, you'll find, small chip, your field of view is really, really narrow, and it actually can get hard to put yourself on target. That long focal length really stresses the performance of your mount. And if you're on one of the commercial fork mounts, you may find it hard to get on target reliably. But on the other hand, there's nothing wrong with a Schmidt-Cass. I used a C11 f10 for a long time. Depending on your camera and your telescope, remember I talked about if your stars are too small, take your focal reducer out. On my C11, I always used an f6 focal reducer. I still ended up with well-sampled stars, and because the seeing was pretty bad where I lived. And it widens your field of view and makes a whole lot of things easier. So nothing wrong with a Schmidt-Cass. plenty of people are using them and getting great results.
Great, that's good to know. Okay, so we had a question that asked if you can explain how did you get that 2 to 3 pixel limit for full width half maximum? And does that limit change if you're binning? I think you addressed that a bit earlier, so you don't have to go over that again.
Yeah, there's if you take the information theory class at your local college, you'll learn about Shannon's sampling theorem. And the idea, gosh, I wish I don't have a whiteboard here. If you imagine a sine wave, a curve that goes up and down and up and down, and you're only going to sample it. So now you have a dot and a dot and a dot. Now draw that on your paper in front of you. And if you're going to use those samples to completely reconstruct the curve, they have to be reasonably close together. If you had at the very bottom of the sine curve, you made a measurement, and then at the very top you made a measurement, and at the very bottom the next time you made another measurement, you could still draw a sine curve through those. But suppose you did those 3 measurements, one at the top, one at the bottom, shift the phase 1/2 of the period of the sine curve. And now suddenly what you've got is, the sine curve is going up and you got a sample right in the middle, and it's coming down and you got another sample right in the middle. So your samples are bump, 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 0, 0, 0, 0. You can't recover the curve from that. So Shannon's theorem says 2 samples per cycle of the highest frequency in the signal. But the hard truth is, in real life, you need usually double that. Hence, 4 samples per cycle. On the other hand, our point spread functions are, pretty well bandwidth limited. So you can get away with 3, but yeah, I like 4 samples per full width half max. You'd be on the safe side. Now, did that answer the question or further confuse the subject?
I guess we will find out. If there are any further questions about that topic, go ahead and submit them. In the meantime, we had a few questions come in about cooled cameras. So one of them was just asking, what about using a cooled camera? And another was asking, what can you do to improve the signal to noise ratio on faint targets? We have been trying to lower the sensor temperatures, but it takes a long time to chill and defrost.
Yeah. Okay, let's talk about what do we mean by signal to noise ratio. Whenever you're making a measurement of anything, there are random effects that influence your measurement. Something as simple as saying, what's the length of this pen? You pull out your ruler and you put it across it. Well, your ruler only has a notch every 1/16 of an inch. You can probably estimate reliably to 1/2 of a 1/16. So that's a 32nd of an inch. And if I said, I want to know the length of this pen to the nearest micron, you couldn't do it. The best you could do is say, well, it's 6 inches long, plus or minus a 32nd or so, plus or minus, say, 0.03 of an inch. And every measurement has that something that creates that randomness in the measurement. Let's call that randomness noise, because you can't predict it, you can't subtract it out. If you measure the length of this pen 10 times, you're going to get, and 10 different people do it, you're going to get 10 different answers. But they're all going to be, within plus or minus 0.03 of an inch of each other. But that's the noise level of that measurement. Now, in photometry, the signal is the total integrated ADUs in the star, say, or equivalently, the total integrated number of photons that you detected. From that, you're going to subtract the sky, so you make an estimate of the sky background. But there's a different sky level on every pixel. A little bit of that is actual change in the sky glow. A lot of it is the fact that photoelectrons are created discretely. You can't have half an electron. And so this particular pixel, photons came in and I got 10 photoelectrons on this image. The pixel right next door, the same number of photons came in, but I only got 9 photoelectrons. There's a randomness to the creation of electrons. There's a randomness to the way the photons come in. And so even though you're now doing an average, that sky background is different randomly from pixel to pixel, and each pixel is different randomly from image to image. And so that's an example of noise that when you say target minus sky, well, I'm going to get a different answer every image, every time because of that randomness. Turns out the signal in your star is also infected by that because it was built by photons coming in. There's a quantum mechanical randomness to that. And your dark current, since you're asking about cooling, same deal. If, as you've seen, your dark signal rises as the temperature of the camera rises and as the exposure gets longer. That you subtract out by having a dark frame. But that dark signal on that pixel, again, is a thermal generation of electrons. Thermal electrons is what dark's made of. And there's a randomness to that at the quantum mechanical level. And so you can subtract the dark signal, but that leaves you with this random level of dark noise. And the way you reduce that dark noise is by cooling the chip. Because if you could get it all the way down to absolute zero, then all the atoms stop moving. And I think at that level, they generate no dark noise, but you can't get that cold. You can only get as cold as your thermoelectric cooler will let you. And ideally, you want to get down to a controlled temperature because if you're trying to get down to minus 20, but the poor little cooler and it's a hot night, it can only get down to minus 10, then it's working itself too hard. And if the ambient temperature changes a little, well, maybe now it can only get down to minus 8. And so your whole noise statistics change. So you get it as cold as you can and as cold as you can regulate it. Once you've done that, you've gotten your noise, you've gotten that source of noise as small as you can. You look at the other sources of noise, maybe sky glow is the next largest source of noise. Well, using a filter instead of unfiltered imaging will help with that. And at some point, the only thing you can do about signal to noise ratio is get more signal, take a longer exposure, or say to yourself, that 17th magnitude nova is just too faint for my gear. So what's your actual situation?
All right. Thank you. And if Patrick wants to elaborate about the situation he's got going on with the cool camera, he's welcome to. All right. So we've got a couple more questions about flats that I think we should go to now. One of them was actually from Patrick Sellip, who asked, do you need to take new flats after changing your focus?
I don't. In theory, there might be a little bit of a change, but I don't know anybody who's ever seen it. So I wouldn't get that picky. But anytime you say remove and change the camera, or get a new filter, or if you clean the optics, you get rid of some of those pieces of dust on the glass, that'll dramatically change your flats. But yeah, focus within reason doesn't seem to have any, like if the temperature gets a little higher, so you need to tweak your focus knob a little. I don't know anybody who's ever seen the flats affected by that.
All right. Thank you.
Of course, now somebody's going to say, well, I did.
That's the way it goes. All right. Our next question is about how do you obtain the flats? Do you do sky flats or dome flats or something else?
Yeah, I have built a light box that gives me a nice uniform flat source into the telescope. And it's not hard to do. Mine's made out of foam board and either LEDs or incandescent bulbs in there. So it's a good do-it-yourself project. And then your challenge is to how do you convince yourself that it's actually putting flat light into the telescope, and so you compare it against a well-done sky flat. Try some t-shirt sky flats to make sure that you don't have any stars in them. And if you can get down to where you're confident that your flat is genuinely flat to within plus or minus 1% or so, that's probably as good as you're ever going to get, and probably as good as you're going to need. Twilight flats are actually surprisingly challenging because you have to move fast because the twilight brightness changes with shocking speed when you're trying to get a whole series of images through different filters and you want 25 of each. The daytime sky is just plain too bright for most of our setups. And so you get a few twilight flats, and then if you can build yourself a light box, that I found that to be the most convenient.
Right. Thank you. Last question here about flats for now comes from Patrick Sellup and asked, should you take darks paired with the exposure of your flats to correct your flats in the same way as you correct your science images?
Yes, absolutely. Yeah, you want flat darks.
Okay.
And particularly if you have a filter wheel with multiple filters in it, the flats through a B filter are going to be way different than the flat exposure through an R filter. So you do need darks associated with each one.
Okay. Thank you. All right. Now I think we're going to go to a question from Mark O'Connell, who had asked, given the start with what you have on hand theme, in your opinion, are the additional complications of starting with a DSLR, which he has, worth the benefits of starting with what's on hand?
Yeah, I do. Because one of the, there are so many aspects to your astronomical hobby that you really need to experience each one and make sure that you enjoy it. I mean, I once had visions of being an astro imager and competing with Tony Hallis, and and after 6 months, I said, I don't have it in me. Mm-hmm. So you're interested in photometry. I'm a strong believer in get an experience with it. If you haven't listened to Barbara Harris's talk about DSLR photometry in particular, listen to it. She knows whereof she speaks, and you can do really excellent photometry with a DSLR. Mine is an ancient EOS, Canon EOS, with 12-bit digitization. So the dynamic range is really constrained. You have to be very careful about your exposures. The Bayer mask, the colored pixel pattern, means that now instead of, say, 4 pixels across your star image, you need 4 sets of the Bayer pattern across it. But that's all doable, and you can do. I have seen people who have made excellent exoplanet transit light curves with a DSLR. So, wow. and the So yeah, absolutely
Yep.
do it. The trickiest thing might be finding software that will do photometry with a DSLR image. I know AIP for Win does an excellent job, and I think some versions of Maxim do.
There was a long discussion on that topic in Barbara Harris's how-to hour. So definitely check out that recording if you have a DSLR and you're interested in getting started.
Yeah, VPhoto does not.
Mhm. All right. And I think that actually answers the next question on the list, which was from Ari Sakura and had asked if it makes any sense doing photometry with color CMOS cameras. And what about doing the same without photometric filters? Given that DSLR sensors are color CMOS sensors, I'm going to assume that the same would apply there.
Yeah, and in fact, you raised an important point that I should have mentioned. If you're using a color sensor, don't add photometric filters in front of it because it's already got a filter array as part of the chip.
Mhm.
Yeah, the colored CMOS, there's no reason to say I can't do photometry. You've got to, do everything that Barbara said regarding DSLR photometry, and it can be done. There's a lot to be said for monochrome in the photometry world, but if a color chip is what you have, do some photometry with it. And if you decide that, man, this is the cat's meow, I want to do more of this, then you can decide whether it's time to buy a filter wheel and a monochrome camera.
Absolutely. All right. Back to something a little bit filter related. Stefan Meister had asked if it's necessary to do your photometry in multiple different bands, for example, B, V, and R, or is usually just a V filter sufficient?
Most people, I think, would use just a V filter. However, as you can imagine, if you do 2 or 3 different filters, you learn more about the star. And there are stars that change color pretty dramatically during their variation. And so I've done, there was a couple of eclipsing binaries that, the 2 stars going around each other. One turns out to be a very red, cool star, and the other a very blue, hot star. And so in the primary and secondary eclipses, the depth of the eclipse is way different if you're in a B or V or R band filter. And it's kind of amazing to see. Plus, the fact that you see it is how you know that one star is blue and the other is red. Having a BVR filter set opens up a whole lot of interesting avenues.
Thank you. All right. So we had a question here from Pradeep Kumar, who asked, how can I standardize the instrumental photometry of a pulsating star using the AAVSO variable star plotter tool, if possible, with an example?
I think Pradeep may be talking about viewing data that's already been collected into the AAVSO database. If that's pretty what you're getting at, the AAVSO database for most stars has data in many different color filters. There'll be usually a great density of points in V band, but there'll be some in B, some in R, maybe some in the tricolor RGB. And when you plot in the variable star plotter, or it's called the light curve generator, you can actually, I think the default is it shows all colors, but you can select, I want only the V band or only the tricolor G band. If, on the other hand, you're asking about, you've taken your own data and you want to put it on the standard photometric system, the key to that is that your comparison star have a known magnitude on the standard system, say a known well-calibrated V magnitude.
Yes, true. Okay, so I'm gonna Oh, hold on. New question came in. No, it was not Pradeep. Okay. So how about I'm gonna say that the interpretation of that, at least for the purposes of getting this on the recording for everyone else, is that using the variable star plotter tool, I believe you can get a list of the precise magnitudes of the comp stars in the field. And then let's just say we're using AAVSO tools, using that and VPhoto. Can you plug those into there to transform instrumental magnitudes to actual magnitudes?
Yeah, VPhoto does transforms. I gotta admit I've never used it, so I can't wax eloquent about it, but it will do transforms for you if you have if you know the color index of your target and if you have images in 2 or more colors.
Okay, thank you. Hopefully that covered all the possible meanings of the question. So talking about AAVSO utilities, our next question is coming from David Marshall, who has asked, is there an AAVSO utility that we can use to determine predicted minima for variables?
Yeah. For most eclipsing binaries, if you go to VSX, give it, search on the binary that you're interested in and go to the detail page for that star, there's the details include the orbital period, the ephemeris, and you can, if you click on the ephemeris, it will give you a list of predicted eclipse times for the next, I don't know, several days or so. I think there is, look at the long period variables section. I believe that there is either a tool or a report that predicts the maxima and or minimum of most of the well-observed long period variables
there. Okay, thank you. And just to add on to that, I believe there's a similar report that's produced and available on the short period pulsator observing section website as well for short period pulsators that can help you figure out which ones will be reaching a fun to observe maxima in the night that you're observing. All right. So next up, simple question from David Lee. What is a practical field of view to aim for when you're doing photometry?
Well, fundamental rule number 1, use the equipment you have. So what field of view do you have? If your field of view is really small, say a 1/4 degree or smaller, you'll have challenges finding comparison stars in the same field as your target. If your target is really bright, then there, like say you're looking at a 6th magnitude star. Well, there's just not that many 6th magnitude stars in the whole sky. And that means you need now a wide field of view to, have a 6th magnitude target and a comp star that's, somewhere in the 6, 7, 8 magnitude neighborhood. And that, so on the one hand, faint stars stress you, you want larger fields of view. And if you happen to have a small field of view inherently, then the challenge of just finding comp stars can be a challenge. But if you have a specific target in mind, look at the chart for that target, and that'll tell you where the well-calibrated comp stars are. And if there's not a couple of good ones in your field of view, check APAS for that location. And there may be APAS stars that have not yet been plotted onto the chart.
All right, that's good advice. Thank you. Speaking about comp stars, I think this will probably be the last question that we get about comp stars tonight. What if you do not have a good bright comp star in the field, but you do have some faint ones? Can you use a multi-star analysis in some of the ADUs?
Yeah, yeah, absolutely, yes. And that, yeah, that happens occasionally. I think you'll find with some of the long period variables when they're near maximum light, there's just nothing near them that's that bright. The term of art is ensemble photometry, where instead of one comp, you use however many you can find. And most of the commercial software allows that. AIP for Win does, Maxim DL does. You can have a half a dozen comp stars, and it will do some sort of a weighted average of the signal in those comps and their calibrated magnitudes to improve the measurement accuracy of the comps. So yeah, the answer is absolutely. Ensemble photometry is good for a lot of reasons.
Thank you. We have a question here from Eric Formosa, who asks, what if there is another star really close by to your target that lands in the annulus? How do you deal with it?
Mm-hmm. Two problems. If it lands inside your measuring aperture, you've got a special challenge. If it lands in the annulus, the first thing to try is see if you increase the gap and move the annulus outward, maybe you can make that offending star land in the gap instead of in the sky annulus. Or maybe you reduce the gap a little and shrink the annulus a little to push that offending star outboard of the annulus. And I think that's the right thing to do. I'm always reluctant to rely on the brain power of the software to deal with a really significant star inside the annulus. But there are in MPO Canopus, there is a tool where you can actually say, this star, I want it removed from my image, and it'll do that. It's really clever and tricky, and Canopus is a wonderful piece of software for photometry. If that interfering star is real close to your target, so close that realistically you can't draw a measuring aperture that excludes that guy, you can include both of them in the measuring aperture, find out the presumably constant brightness of that interfering star, and then adjust your photometry accordingly. I'd say that's not a game for beginners. It can go wrong in a whole lot of ways.
All right.
So, but the annulus is one where, an interfering star is pretty common, and just, adjust your annulus size to try to eliminate it.
All right. So speaking in a general sense about software there, let's go to this question from Jane Lubinsky, who had asked if you can use the software ASTAP, that's ASTAP, for photometry.
Oh yes, I saw that question when it came in, and I must confess I've never heard of that software before. If it has a photometry routine in it, it's probably doing differential photometry based on measuring apertures exactly as described.
All right.
Many of the astroimaging packages do.
All right, so we have a couple of questions here that are about supernovae in a roundabout way. Tetsuji Tanika, I'm very sorry if I mispronounced your name there, had said that supernovae are always occurring near galaxies. And do you have any good idea about removing the contamination from the host galaxy?
Yeah, the easy way is if your field and your measuring aperture and your annulus are all tight enough that the background glow of the galaxy is, pretty much just a smooth glow. Hey, it's just sky glow. And the whole aperture photometry theory will work. My guess is that's what most people do, is just treat the background glow of the galaxy as if it's just enhanced sky glow. I got involved in a project a couple of years ago where we were a little worried about the modeling, the variation in the galaxy brightness, even over the size of our measuring apertures, and went to an enormous effort to do a sort of a curve fit to the brightness versus position in the image of the galaxy, and then subtract that out. And after all that work, the answers were almost indistinguishable from what normal aperture photometry gave us. So,
all right, that's good to know.
Your mileage may vary.
Next question about supernovae is not really about the supernovae themselves, but HM Sucker says that his interest is supernovae, so he often needs new comp star charts, and he's really surprised at how quickly those charts are provided by the AAVSO. So he wants to know how many people are working on this.
I don't know, but you're absolutely right. The sequence team is Johnny on the spot when there's an interesting new transient discovered. And they work hard and efficiently and accurately, and their efforts are a real credit to the AAVSO and a real service to the community.
Yeah, that's the truth right there. All right, so next up, a couple of technical questions. One was from Jim Jonsky, who asked, can you automate effectively to do nightly photometry?
Oh yeah, absolutely. If you can script your observing system, so you can tell the mount, I want you to go here and do this image sequence, and then go over there and do that image sequence. Absolutely, because your job is to take good photometric images of the target. I have a friend who is really interested in asteroid light curves. And most people, because the asteroid light curve changes relatively rapidly, you need an image every few minutes, and usually people stay on them all night. But he has automated and scripted he's on an AP mount, scripted the setup so it will go to asteroid number 1, take a dozen images, and then go to asteroid number 2 and take a dozen, and then number 3 and take a dozen, and then back to number 1. And so he's just a monster at productivity on that subject.
Nice. Okay. Yes.
If you need to initiate guiding at each place, then it's a lot more troublesome. He's got a good mount, and I'm pretty sure that he is not guiding. He's taking unguided images. And by the way, as Barbara Harris, I think, has pointed out in connection with DSLR, it's also true in CCD photometry that as you get experience, you will be astounded at how poor your image can be and still get good photometry from it. If your stars are a little oblong because your mount didn't track perfectly and you weren't guiding, if you make your measuring aperture big enough to capture all the light from the star, you're probably going to still get excellent photometry.
All right. We're getting down towards the end of the questions here, so a couple more technical ones first. How many dithering shots do you take for an observation?
That's an interesting question. I don't dither.
Okay.
I know it's very common in the astro imaging world. And part of the reason I think in photometry it's much less common is because we insist on blobby stars. And so I'm not sure that dithering would really buy you very much in photometry, but I have no experience.
I know that in slitless spectroscopy like I do, that helps to reduce the noise somewhat by spreading it across multiple pixels, but also um, you're stacking a ton of frames, and I don't know, it's a little bit different situation from photometry. So that might be the reasoning behind asking, is spreading out some of the noise, but then you're already subtracting darks and flats. So
yeah.
all right. So if the comparison stars are outside of your field of view and your field of view is too narrow, are you allowed to move the telescope and shoot a second image to record the comparison stars?
You know, it's funny. The CCD photometry community acts as if that is just, don't do it. But the photoelectric photometry community, that's exactly what they do. I aim because they've got a field of view that's like 0. And so, I might target, and then I go to a comp, and then I go to the sky, and then I go to the check, and then back to the target. So I got to admit, I don't think I've ever tried that. And as you can imagine, there are dangers there. What if the atmospheric extinction changes a little between, looking at your target and looking at your comp? If you have to do that, spend a night with something like M67 and get a sense. If I go to the cluster, and then I go off the cluster, and I go back to the cluster, and if it turns out your photometry is still good accuracy and good precision, there's no law against it. It's just you're losing one of the great conveniences of having an imaging sensor. Mm-hmm. And it sort of demands that you have a much cleaner night. If there's a little bit of scattered cirrus across the sky, that method's just not going to work.
Right. All right. Thank you. Let's see. We had a question here that from Jane Lubensky, who had asked, if you incorporated a slit into the light path, presumably somewhat like a spectrograph, would it facilitate measuring the magnitude in a really dense star field where there's contamination, or like a supernova on a galaxy, as discussed earlier?
Yeah, probably could. Maybe a slit, maybe an occulting bar, like the double star observers use to block a really bright primary. On the other hand, everything that I talked about was aperture photometry. For dense star fields, there's a whole different technology called point spread function fitting photometry, where you can recognize that this blob has 2 peaks in it. So even though it's one blob, it's 2 stars, and you can start unraveling that with point spread function photometry. To my knowledge, there is no common commercial software package that does that. The professional astronomers use a package called IRAF, and in it is an identification tool called Star Extractor. And Sextractor will do that. So it can be done. It's common in the professional astronomy world in dense star fields like that. But unfortunately, I don't know of any easily available commercial package that will do it.
Okay, thank you. All right, just a couple more questions now. One was from Stephen Future, who asked, what magnitudes do you use for your reference stars when you're shooting with a filter that is not quoted by the AAVSO?
The filter you use and the magnitudes you use are actually, kind of 2 different things. So if your filter is anywhere near V-band kind of sensitivity profile, and I use that very broadly, to include maybe a totally unfiltered CCD. If it's anywhere near that, use the V-band magnitudes and report them as such. Because you're comparing the light you received from the target and the comp and the V magnitude of the comp. That's a little bit of a fuzzy answer, but that's the best I can do off the top of my head.
Okay, thank you. All right, John Merle had asked, are the responses of CCDs and CMOS to wavelengths similar enough that you don't need to do a transform, bearing in mind that a lot of CMOS chips are backside illuminated?
Yeah, if you look at the performance curves of different chips, there's surprising differences in spectral sensitivity curves. The first thing you look at is the peak quantum efficiency 60% or is it 85%? But then as it sounds like you've done, you look at the bumps and wiggles in that spectral response curve, and they're very different. I haven't seen anybody try to do a transform, say from an unfiltered CCD to an unfiltered CMOS. And I think the reason for that is it's hard to figure out why you would want to. Normally you own a camera and you want to know how different its photometry is from the standard Johnson Cousins or standard Sloan passband. And so you're kind of only interested in your response and the standard response of those photometric surveys. I mean, theoretically it could be done, but I'm not sure.
So
maybe I'm missing the point.
Right. So then I summarize that as just the goal is to get your points to match the photometric standard and not regardless of what camera you're using.
Yeah.
Okay. All right, 2 more questions. So first one is from Tapio Lehtinen, who asked if you can give any concrete examples of variable binary stars with extremely different star colors for us to observe.
Off the top of my head, yeah, BO Mon. BO Monoceros is a quite blue star and a quite red star. And in the primary eclipse, not only does the brightness drop noticeably, but the color changes noticeably. And it's a kind of an interesting system for a lot of reasons. But one reason is if you say set your camera and filter wheel up to go, B filter, R filter, V filter, B, R, V, and just take a series of images through that sequence through an eclipse. You'll see how not only does the brightness drop, but the B minus V and V minus R colors change pretty noticeably.
All right, very cool.
The bad news is I don't remember what brightness it, but when in full eclipse, it gets pretty faint. It's probably somewhere in the 12, maybe 13th magnitude neighborhood.
Okay. All right, our last question here comes from Fabio Bradash, who has asked if there's some sort of repository somewhere of images to play with and practice on a rainy day.
That's a good question. Not that I can think of off the top of my head. But if you have any astro imager friends, you want to play with your photometry software, the star in it doesn't actually have to be variable. So, have them send you their images of M67 or M35 and in FITS format and go to town. Lauren, you might remember, does the exoplanet database on AAVSO include images of the planet field?
I don't recall if it does. When I poked around it myself, I was only seeing light curves, but I don't recall for sure.
Yeah, I don't know of one off the top of my head.
One resource I'll take this opportunity to mention is the Bright Star Monitor telescopes. I'm not sure if it's only, it might be only AAVSO members, but you can submit a proposal, just a star that you would like to be observed, and one of the Bright Star Monitor telescopes will observe that variable star and put the FITS file data into your account, where if you're an AAVSO member, you can directly upload that to VPhoto and get to processing that way. And the images are great quality. So it's a good way to practice just the software side of things with photometry without having to worry about the hardware side.
Mm-hmm. Good idea.
And that right there was our last question. So I'm going to go ahead and close the webinar. We got some closing announcements.
Thank you for your interest, everybody. This was fun for me. I hope you enjoyed it. Thanks, Lauren.
Yeah. Thank you. All right. So first closing announcement is that I would like to extend a huge thank you to you, Mr. Buchheim, for sharing your time and knowledge with us today. All right. And I would also like to thank our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO Net Observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey Project, also known as APAS, which has been discussed quite a bit tonight, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields hands-off at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The remaining 1% is where Mr. Buchheim's variable star was. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Today's how-to hour has been recorded, and the recording will soon be made available for free on the AAVSO's YouTube channel, where you can find a full library of webinars just like these. Go check it out, and while you're there, consider subscribing to our channel. Not only will you get a notification every time that a new lecture, how-to hour, or webinar is posted, but by hitting that little subscribe button, you will be increasing our educational reach. YouTube will be more likely to suggest our videos to others and bring other people into the CCD Photometry fold. This is just one more way that you can help support the AAVSO. Speaking of support, this webinar series is being supported by you, the viewer. So please, if you're not a member, join the AAVSO. AAVSO membership comes with a wide array of benefits, from our excellent VPhoto software all the way to our mentorship program. Our mentors can help you get started on your journey into CCD photometry. So if you're left still feeling a little bit confused or intimidated, which I don't know why you would be, but if you are, join the AAVSO and check out our mentorship program. And as always, we would be so grateful if you would consider donating to the AAVSO. Every donation matters and goes towards making programs like this come to life. That QR code on your screen right there, if you hold your phone camera up to it, then assuming you have one of those smartphones, it does a creepy thing where it pops up the web page where you can donate. All right. One last thing before you go. After you leave the webinar, you will be automatically directed to a survey. We will really appreciate it if you fill it out, even if you've already filled out a survey at a past AAVSO webinar, because what we're doing is we're collecting and every single response, reading them individually, and using the feedback to make plans that will shape the future of the webinar series, looking at how the trends change over time, doing our own variable star analysis almost on that. Do take note that the survey is anonymous. So if you use it to ask any questions that you want to receive a direct reply about, Make sure that you write down your email address or another way to contact you in the text box down at the bottom so that we know who to send our reply to. Finally, I would like to extend one last huge thank you to Mr. Buchheim from all of us at the AAVSO. We appreciate you.
Thank you very much, Lauren.